Welcome to Lesson 11 of the PID Control course. Today's lecture is going to be special because we will not only learn theory, but also understand the real industrial behavior of PID control. First, let's quickly see what we will learn today. Today, we will understand how the parameters of PID are defined in an industrial context. A very common problem, integrator windup, ways to apply derivative control, and a very important concept, bumpless auto-manual transfer. Finally, the digital implementation of PID. So, let's start with the PID equation. As you have learned before, the PID controller is made up of three parts: proportional, KP, integral, TI, derivative, TD. But today we will understand them from a slightly different perspective. First, let's talk about the proportional gain, KP. What does KP do? It immediately gives output based on the error, meaning the more the error, the more the control action. But in industrial systems, another term is used, proportional band, PB. What is PB? It is the range of error in which the controller output changes from 0% to 100%. In simple terms, PB notch 100 KP. Meaning, if KP is high, PB will be low. If KP is low, PB will be high. Now let's take a small example. Let's say there is a temperature control system with a full scale of 50 degrees Celsius. If the heater goes from 0% to 100% with just a 2 degree loss error, it means that the proportional band is very small. Now, let's move on to integral action. What does integral do? It continuously adds the error over time. Its purpose is to eliminate steady-state error. Now, here comes an interesting term. Integral time, TI. The meaning of TI is the time in which the integral action becomes equal to the proportional action. In simple terms, after every TI time, the integral part will have the same effect as the proportional part. Now let's talk about derivative action. What does derivative do? It looks at the change in error, meaning how quickly the error is changing. It preempts the system so that overshoot is reduced. Now let's come to the most important topic of today. Integrator wind-up. This problem is very common in industrial systems. Suppose your actuator is limited, meaning it cannot give more than 100% output, but the controller keeps trying to give more output. So what will happen? The actuator will saturate, but the integral part will keep adding the error, and this is where it starts. Wind up. In simple terms, the controller thinks, I am increasing the output, but in reality, the actuator cannot do anything. During this time, the integral value increases significantly. Now, when you reduce the set point, ideally, the output should decrease immediately, but it doesn't. Why? Because the integral is already charged too much. That's why the system responds slowly, and there is a delay. This is called integrator wind-up. Now, the question is, how can it be stopped? The solution is anti-reset wind-up. What do we do in this? We monitor the actuator output, and as soon as saturation occurs, we stop the integral from increasing, meaning when the actuator and output cannot give, the controller will not force it either. What is the benefit of this? Fast recovery, no delay, smooth control.